Okay. All right, let's get started. So I'm Jason Arhart. I work at Originate. I started playing with Scala in, I think, December of 2009. And I immediately liked it, and I'm fortunate enough now to be able to do Scala as my day job. At Originate for about the last 6 months, Scala is all I've been doing. So. I'm going to be talking about the reader monad, using the reader monad for dependency injection. Specifically, I'm going to, well, let me start by what I'm not going to be talking about. This is not about why the reader monad is the right approach to dependency injection, because I don't think there's a right approach. It might be the right approach to you. It might be the right approach for a particular application. I happen to like it for a little bit that I've done with it. I'm also not going to talk about the right way to do dependency injection with the reader monad. I'm going to talk about a way that I figured out how to do it, but I'm certainly no expert. What I am going to talk about, I'm going to start really briefly with why we care about dependency injection. I'm not going to spend much time on that. I figure if you're here, you already have an answer to that question. And I'm going to go over just a quick review of monads in Scala, like how Scala sees monads. And then I'm going to introduce the reader monad, and then I'm going to talk about how to apply it to dependency injection. Me and a colleague of mine did a little small project to try it out, and discovered a bunch of sorts of problems that you can run into, and came up with solutions. So I'm just going to be talking through those. So why dependency injection? So let's look at a real simple diagram of a possible architecture for a application. If if an application has any sort of architecture at all, a lot of them I've seen have been basically a layered approach, where each layer depends on on the next lower layer, which it kind of makes sense. The problem with this is the higher level layers are coupled to the lower level layers, which presents a number of problems. First of all, any change you make to the lower level layers affects all of the layers above it. Secondly, this coupling means that, like in this case, the service layer can't really exist without the persistence layer. So you can't, for example, take it out and test it in isolation, because you need to bring the persistence layer along with it. And this is especially a problem with most applications have several layers. So Bob Martin and the guys at Object Mentor kind of noticed this problem and came up with a solution called the dependency inversion principle, which and this comes straight from Bob's paper on this. It says high-level modules should not depend upon low-level modules. Both should depend upon abstractions. And then abstractions should not depend upon details. Details should depend upon abstractions. This is like most of the quick descriptions of the solid principles, in that it makes perfect sense if you already understand the principle, but it's not much help if you don't. But basically, all it says is instead of having your higher level layers depending directly on your lower level layers, just put an abstraction in between them. So in this case, we have the service layer actually depending on a persistence interface instead of directly on the persistence layer, and then the persistence layer also depends on the persistence interface in a different way. And this lets you decouple the modules from each other. So like every solution, this creates a new problem. How do you wire those modules back together? After all, an abstraction doesn't compute anything. So to actually run your application, the service layer, in this case, needs a concrete persistence layer. So yeah, how do the high-level modules access the low-level modules? Back in, I think, the late 90s, the way people the idea people had for doing this was to have the application live inside a container, and then it would have some sort of knowledge of the container, so it could reach out to the container and say, hey, I have these dependencies, can you give me a concrete implementation? This caused some problems, because now your application is coupled to the container it lives in. So again, it makes it harder to pull it out and test it, and causes other problems. So then some people came up with this idea with some fancy terms like inversion of control and dependency injection, which basically said flip it around, make it the container's responsibility to give the application its dependencies. And they call this dependency injection. Most of the time this just really means there's a parameter you pass to a constructor or something. So before I talk about doing dependency injection with the reader monad, let me just quickly review how monads work in Scala. So let's start with one of the simplest that probably most people are familiar with is the list monad. So you can create a list, and then one of the things you can do with the list is you can map with it. In this case, we're mapping a function literal that just squares its arguments. So you take a list and turn it into you create a new list of in this case of the squares of the numbers in the first list. And Scala gives you some nice syntactic sugar for this. You can write this as a comprehension, which in some cases can look a lot better. And the signature of map on list looks somewhat like this. This is a simplification of the actual signature, or depending on who you ask, a lie. But basically the concept is you have a function it takes a function from A to B and turns a list of A into a list of B. And this map operation has some properties. The first one up here is the identity property. If you take any list and map with the identity function, does everybody know what the identity function is? Anybody not? So the identity function is just a function. It's just a function that does nothing to its argument. It just returns its argument unchanged. So if you map with the identity function, the list you get out is equal to the list you started with. And then there's an associative property where with any list, if you map with the function f and then map the result of that with the function g, you get an equal list to if you take the list and just map with a single function that's the composition of f and g, where it applies f to the argument and then g to the result. So this signature for map along with these properties make list a functor. Now we can also flat map with list. So flat map, instead of going from element to element, you go from element to sublist. So you overcome the restriction. So map has a restriction that you can only turn a list of some size into another list of the same size. With flat map, since you're mapping to sublist, you can change the size. You can change it to any size. You can combine lists in different ways, and Scala also has some nice syntax for this. You do a multi-level for comprehension, and flat map has a signature that, again, simplified, looks like this. It takes a function from A to a list of B and uses that to turn a list of A into a list of B. And flat map has a relationship to map, where if you flat map with a function that applies f and then sticks it in a singleton list, that's exactly equivalent to just mapping with f. And it has some properties. It has two identity properties and an associative property. The first identity property basically just says if you take anything and stick it into a singleton list and flat map a function f, it's equivalent to just applying f to that element. And then the second, that was left identity. The second right identity property falls directly out of the identity property for functors and the relationship of flat map to map. And that if you flat map with the function that does nothing but stick its argument in a singleton list, you get an equal list back out. And it has an associative property which says if you flat map with an f and then flat map the result of that with a g, it's equivalent to flat mapping with a function that applies f to its argument and then flat maps g to that. So these two signatures for map and flat map, along with all of these properties for how they operate and relate to each other, make list a monad. So now we're gonna kind of like circle in on the reader monad. We're gonna put monad specifically aside and talk about functions, specifically unary functions in Scala, first-class unary functions. So you can create functions. Here we have a function that just adds 2 to its argument. And then we can also write it with the shortcut syntax. And you apply it to a value, and you get the result. You can also create functions from methods. In this case, we have a method add that closes over an x argument and returns a function that adds x to its argument. And then we can create our add2 function using this method, and then it works the same way. And then a really cool thing about unary functions is they can be composed with this and then method. So and then actually does exactly what it sounds like. It creates a new function that applies the first function and then applies the second function to its result. So I really love how this reads, like add 2 and then multiply by 3. It says exactly what it does. So we apply this to an argument, it does that. It adds 2 to get 5 and then multiplies by 3 to get 15. Now, and then has some properties as well. It actually has an identity property. And in particular, it has an identity property and an associative property. And these are actually exactly the functor properties. So technically, unary functions in Scala under composition with and then make a functor. It's just not called map. So we can use and then like this, but we can't use map like that because it's not defined on function in Scala. So we can't use the nice for comprehension syntax, and it doesn't have anything like a flat map. So enter the reader monad. So the reader monad is just a wrapper around unary functions. It uses and then as map, and then it defines a flat map that makes sense. And it's actually really simple. You can one way to implement a reader monad is like this. Map just wraps a function in a reader, and map is defined as and then flat map just does map and then flattens it by using a function that takes its argument and applies it twice. But there's no reason to really implement this thing. Scala Z has a really good reader. It's got it's a very full-featured reader with a lot of other things that like Haskell programmers expect a reader to have. So just use Scala Z's reader. So with the reader, we can then map like we wanted to with the function, and then that gives us the ability to use for comprehensions. Okay, so what does this have to do with dependency injection? So let's look at another reader. Here we have a reader that wraps a function that takes a user repository and gets a user out of it. This thing here, the user repo, that's a dependency. We've actually got a function that has a dependency, and we get a reader, and we can inject it just by calling it with that dependency. And because readers are monads, they're composable. They're very composable, so we can define other readers in terms of simpler readers. So this is just a simple example where we get the user and then get the user's email. And because it defines flat map, we can even do multi-level comprehensions with it and do fancier things like get a user from the repo and then use something from that user to get a different user from the repo. And all of these are just readers. You give it a user repo, it'll give you what you want. And so basically the way this looks in practice is you might have a dependency that has a number of operations, and then you just define a reader for each one of these operations, and then you just compose the rest of your application logic out of these readers. But I don't exactly like doing it this way. I have 3 operations, and I'm creating 3 different primitive readers. Readers are so composable, I like to have as few primitive readers and compose the rest out of those. So one way to do that is to just create one top-level reader that just wraps the identity function, and now I can define the other readers by just mapping over that. And this is exactly equivalent to the way I had it on the previous slide. So what about other dependencies? I have yet to write an application where the only dependency is a single user repository. So, and reader only takes 1 argument. Well, that's simple enough to solve. Just aggregate the different dependencies. So we can just create a trait like repositories that contains a number of repositories. And then in a companion object, create again an identity reader that just given a set of repositories just returns that set of repositories, and then we can create readers for the specific dependencies based on that. And then the only thing that changes in our actual operation readers is we just change that our primitive reader that we declared there to an import. Well, technically that's the only thing that, well, it looks like the only thing that changes. Technically, all of the signatures of all of these change because they're returning reader from repositories instead of reader from user repo. And then we can go a level further and just declare all of our dependencies inside a top level trait, environment trait. And then, of course, do the same thing, create readers for everything, all the dependencies that are defined in that. In this case, then we can just change the repository, the top of the repositories to an import. And then what we have to change, that. And then what we have to change here with user repo is nothing. It stays just the same, but again, technically the signatures change. So now everything is a reader of the environment. So what we have now, we've defined this single top-level reader for the environment that wraps the identity function that just given an environment, returns an environment, and we've used that to create readers for all the other dependencies. So we've got readers that given an environment will return a specific dependency out of that environment. And that kind of abstracts away the structure of our dependencies. We can structure it any way we want. The code that uses it doesn't have to change because it's just using the reader that knows how to get the thing out of the environment. So then our service, our next layer just looks like this. We can, we've kind of seen these methods or something like them already. You just do for comprehensions over the reader, and this doesn't look like we're doing anything particular for dependency injection. It just, these methods are all returning readers that we inject an environment and we get the result of whatever it's written to compute. And this is concrete. These are defined in an object, and we can call these methods anytime we want, and we just get a reader at any layer of our application. The whole application is just defined in terms of these readers. We can just call the method to get a reader and then inject the environment to get what we want out of it. And then one final kind of thing to make that nice that I like to do is put all the dependencies in their own component like that. So then I can define the structure of the environment by just mixing traits together. It's nice and clean. And that allows me to define implementations of each component in separate traits, and then just mix and match them together to create my actual environments that I want to run with. So what about using other monads in your application? At Originate, we do most of the Scala we do is we mainly use Scala for web applications, and we use the Play framework typically. And the Play framework likes things to be asynchronous, and we like things to be asynchronous. And our repositories usually don't look like this. They look more like this. They return futures. And future is its own monad, and throw this into the mix with the reader monad, and then you get a kind of a tangled mess when you try to flat map over one and map over the other. So for example, our get email changes we can't do this anymore because get user, we're not getting a user out of get user anymore, we're getting the future of a user. So we have to basically map over the reader to get a future, and then map over the future to get the email out of that. Which it's not horrible, but it's more than I want to do. It's more than we have to do. And when you have a multi-level comprehension where you're doing flat map, it's even worse. The cleanest way that I could figure out how to do this was to actually map over my top-level environment reader to get a binding to an actual environment, and then actually do a flat map over the future itself by actually running each reader with the environment to get the future. Again, it's It's actually not as bad as I thought it would be, but it's way more boilerplate than I'd like to write. I mean, this would basically be, all of your methods would have all of this wrapped around it. So there's a solution called monad transformers. So the basic problem is our methods like find user, the signature here is a reader from environment to a future of user, which has a signature, which has map and flat map signatures that look like this. And the key problem is right here. This parameter is a future. We would like to have something that has where the map and flat map parameters are just whatever's in the something. And we can do that by changing from a reader of environment to a future of user to a reader T of future and environment and user. So a reader T, so this reader T wraps the exact same type of function. It wraps a function from an environment to a future of user, but it lets us map and flat map directly over the thing that's in the future instead of the future itself, which is great. It's what we want. So our find address, once again, just looks like this. One slight wrinkle, and this, as far as I know, this only applies to the reader transformer in Scala Z. It doesn't apply to any of the other transformers I know of, is that we can't just create this by saying reader T and trying to wrap a function, because it turns out that a reader T is the same thing as a Kleisli arrow. And the Scala Z people decided to define the Kleisli arrow and then make reader T just a type alias to Kleisli. So simple solution, Scala gives us, so we have to write it actually like this. So if you don't know what a Kleisli arrow is, don't worry, just whenever you see that K word, pronounce it reader T. But Scala gives a solution to this in type aliases. In dealing with monad transformers in general, and with the reader transformer in particular, type aliases are your friends. So in this case, I created a type alias for it called query. It made sense for the application we were working on because the only thing returning futures were actually database queries. And then I defined an apply on query that let me wrap it the way I want, wrap the function the way I wanted to. And then I defined a method lift that'll take a reader from an environment to a future of something and lift it into a query. I'm not sure lift was actually a good name for this, but functional programmers seem to like to lift things, and it seemed appropriate. So then we define our user repo like this. Basically, the only thing that changes is Scala futures need an implicit execution context, and then we just use query.lift for all of the operations. And then our user service looks like this. It looks pretty much exactly like it would look if we were just working with futures and not the reader monad, except, yes?
Why don't you pass the execution context in the environment?
I could do that.
It's like mixing and matching two different ways.
That's a really good point. I hadn't thought of that. That might make a lot of sense. The only thing I can think of is you might want to use different execution environments and different. If you have certain operations that are really quick, you might want to use a execution context with a small thread pool, and then database operations might have a different thread pool. Oh yeah, that's a good point. Yeah, so that's actually a great idea. So, yeah, that's a great idea. Thank you. What's that? Oh, I'm sorry. Yes, he was asking, why am I using why do I keep passing around the implicit execution context? I'm basically mixing dependency injection techniques. Why not put execution context into my environment and use the reader monad? And that's a great idea. There's no reason not to do that. I just hadn't thought of it. I'm just so used to having that implicit argument when I work with futures. So the only thing you have to know is when you're using monad transformers, when you're transforming a monad with Scala Z monad transformers, you have to have an instance of the Scala monad type class for the thing you're transforming. And so in this case, we need an instance, we need a monad instance for Scala's future, and you can get one of those from Scala contrib, and you just have to have this import so that that type class instance is in scope. What's the next slide? Okay, so we've talked about all of these readers, and basically so far all we've been doing really is creating this thing where we have all of these readers, and we've just kind of been deferring the actual dependency injection. So I haven't talked about how to actually get the dependencies into the readers in a real application. And so what I came up with for our play application was I just created an abstract controller class that takes the environment as a constructor parameter, and then I define some run methods that just run the reader with that environment. I don't know if I mentioned it. I just don't want to skip over the run on a reader. Just basically applies the run actually is the function that it's wrapping. So what I'm doing here is just applying the environment to the function that the monad wrapped. You can also just use apply, but I was using the implicit execution context, so it kind of gets in the way of using apply, which now I have a solution for. So then in the actual controller, I just extend that abstract controller class, import the things I need, and then in my actual controller actions, I just run the reader. For a while, I was trying to figure out a clever way to make my own sort of composable action things that would do this for me, so I wouldn't have to have that run in my actions. And then I realized I was going through a lot of trouble to try to make it easy to put a lot of application logic in my controllers, which I don't want to do anyway, so I decided that this was actually better. And then the Play framework has a nice facility, I think starting with Play 2.1, has a nice facility for using dependency injection for controllers, using whatever dependency injection you want, where you just have to override this get controller instance. So in your global settings. So in my global settings here, I just define an environment to run with, and I just define get controller instance. So it takes a class. This is the class of the controller, and I find a constructor for that controller that takes the environment, and I just create a new instance. I'm just using Java reflection here. And then in the routes file, you just put this @ sign in front of the action in your routes file, and that tells Play to invoke that dependency injection mechanism. All right, so one of the motivations actually for dependency injection is easier testing. So how do we do that? So the way I did it, I just created a bunch of components. This is one of the reasons I liked to break out have the components for each dependency and break them out. I can create these test components that just mock up the dependencies. And then I can create my mock environment that just mixes all those together. Now I made this a class because in tests I want to be able to create a new instance of all of these mocks for each test that I'm running. Otherwise I can stub some things and it'll affect other. You don't want to have. You want to use fresh instances of your mocks for all your tests. So then I created a helper, a test environment helper, where I define an abstract environment. So this might not be strictly necessary. I put it there so that I could, in some tests, if I don't want if I want to test a particular dependency that's using another dependency, I can not mock that, but mock the other ones. And then I defined an await helper that awaits on a query instead of a future. And so in my test, what it looks like is I define. I make a scope trait for my test that mixes in the test environment, and then I create within that I instantiate a new mock environment for each. This will be instantiated for each test. And I define some test objects to play with, and then what the test looks like is I mix in that scope trait and then set up my mocks and then just use a weight to get the actual result and make assertions with it. And that's about it. Any questions? Yes? Okay, so the question was why is this better than just passing arguments to the function? The main thing is essentially it is passing curried arguments to the function. It just it hides it away. So I'm not actually seeing those. Let's see if we can go back to. So here, in my method signatures, I'm not actually the fact that I have this reader parameter or this environment parameter to pass in. I don't have to have that in my signatures, and I don't have to keep threading it through each call. I just like it better. Okay. Anyone else? Yes. I didn't really create a big enough application to really know that, so I don't know. I actually don't know if there. Oh, so the question was, are there any performance problems with creating all of these closures? And the answer is I really don't know. I didn't create a big enough application to really drive that out. Anyone else? Okay. Thank you very much.